Okay, thank you very much. I would like to thank the organizer for giving me the opportunity to give this talk. So I present results of studies which I did with my PhD student Chandra Shekhar. So we studied tomographic cross correlations between CMB lensing and galaxy surveys, and in particular we studied systematic errors which comes from crosstalk between redshift beams of the galaxies. So why these studies are interesting? So from Planck data we have map of CMB lensing potential. So it gives us information about distribution of dark matter in the universe. So this lensing effect is simply a secondary effect related with large structure for our universe, which simply deflects parts of CMB photons. So we have on average standard deviation of such deflections of 3 minutes, and from correlations of these deflection angles we can reconstruct this lensing potential. This is what was done with Planck data. So we can trace distribution of dark matter. Here is actually lensing kernel for CMB data. So we see this actually is this line of sight integration of gravitational potential using lensing. So problem is, if you want to really study evolution, time evolution of this lensing potential, we don't know exactly which redshift has this object, quite wide redshift range from 1 to 6, 7. So we need to cross-correlate these maps with some tracers of objects with known redshift. So, for instance, galaxies, quasars, radio sources. And then having redshift distribution of such objects, we can split on redshift beams this redshift distribution and study time evolution of this correlation. So currently it's called this field cosmic tomographic, and it's now there are many papers dealing with this topic. So in our work we use angular cross-correlation power spectrum. So here is theoretical expression for this power spectrum. It's simply integration and line of sight of power spectrum of matter and weighted by some kernels for lensing convergence field, which is simply Laplacian of the lensing potential, and density contrast of galaxies. So here are the kernels for galaxies and simply redshift distributions times bias. So this is shown this line here. So we actually, the most important question which we wanted to answer in the studies is how we can measure cross-correlation in different redshift beams given photometric redshift errors. So because of these errors, some objects will be assigned to different beams, but they have true redshift. So question is does it really have some impact on our estimation of cross-correlation for different redshift beams or not, and how important is this effect? So we use simulations to test it. So for some future galaxy surveys, in particular we use science book of LSST experiment. So we generated 300 simulations of correlated log normal galaxy over the CT field with CMB lensing convergence field, which was consistent with the Planck CMB lensing map. And we use for these simulations full sky log normal astrophysical simulation kit, so-called Flask code, published a few years ago by Xavier and others. So this is simply code which allows to simulate correlated fields in for different redshift shells, as shown in this figure. And so we did such simulations for different redshifts. So having the simulations, we we know true redshift distribution, we know true redshifts of all objects, so we can really do tests properly because we know what are true cross-Pawel spectra and so on. So having this true redshift distribution is related with redshift distribution for objects with photometric redshift by this convolution. So here is an error function for photometric redshifts. It's simply, we assume it's Gaussian with the mean centered on true redshift and the standard deviation given by these expressions. So, so we can then do tomographic binning of this true redshift distribution. So here are these bins shown by these vertical lines. We have nine bins, and then we translate into distribution in photometric redshifts by this convolution. So these are the solid lines here, for different bins. So, and we did this test for two values of the sigma 0 standard deviation corresponding to value from science book of LSST and a little bit larger value, which is, I think, for many experiments right now, corresponds. So, and with this, here is this window function, so it's simply a top hat function. So, question is how we can relate angular power spectrum for data, which for data we have this objects with photometric redshifts. So we measure angular power spectrum for photometric redshift objects, while we have true angular power spectrum for objects with true redshifts. So what is relation? So this relation was given in a paper in 2010 by Zhang. So this is this relation. So these quantities are related by so-called scattering matrix. So it's simply a fraction of objects from true bin I, which is wrongly assigned to bin J, over total number of objects in bin J. So we have this is relation for autopower spectrum from galaxies, and here's for cross correlation with the convergence field. So we see here is quadratic function of this scattering matrix. Here is ideal function. It will have some impact, and we'll see results. This is more, this autopower spectrum is more sensitive to precision with which we can estimate the scattering matrix, while this cross-power spectrum is less sensitive. So in 2017, Zhang proposed algorithm to estimate this quantities, this scattering matrix and true power spectrum, having this observed power spectrum for objects with photometric redshifts. However, this algorithm is quite complex and numerically quite demanding. We use our method. We simply try to estimate true redshift distribution from this photometric redshift distribution. So from this relation, we have this photometric redshift distribution for observed objects, and we do deconvolution, because it's a deconvolution of this equation, and look for this true redshift distribution. We tested it on simulations and with various, not only for such smooth distributions, but also with some wiggles which are more realistic, and it looks like this method works pretty well. So we are in principle able quite well reconstruct this true redshift distribution using this deconvolution, and then we can estimate this scattering matrix quite easily. And here are simulation, based on simulations, we see how the scattering matrix looks like for different values of photometric errors. So we see here diagonal terms, but off-diagonal terms of order few percent in this case, and here we have of order of several percent, and also we see there are not only here are zeros after only this neighboring bins we see some non-zero scattering matrix elements, but here we see also for elements which are beings which are more far away from this being which we are talking about. It's nothing surprising, because if you look well here, this neighboring, here we see only this tail go to this neighboring beam, right? So in principle, the scattering matrix's values corresponds to area under this tail of distributions in neighboring beams, right? And here we see some of these tails go even to two beams away from a given beam. So we see it in the scattering matrix for this prototype. And we tested having simulations. We know what is true scattering matrix, right? Because we know all the redshift everything. So we know true, and we can compare with this method of estimation of scattering matrix which we use, and we see very small errors, very small bias. So we are pretty convinced that we are doing well with this. And actually in literature, I showed this references to other papers. In literature, actually this method using scattering matrix is not actually used. And in many papers it's used, I would call it naive approach, where we simply, to model a power spectrum for photometric redshift objects, we simply replace redshift distribution, this true redshift distribution, by redshift distribution for photometric redshift objects, and we say this is our power spectrum. However, we see here we don't take into account these correlations, which takes into account scattering matrix between different redshift beams, right? Because we can have some objects which are wrongly assigned to other redshift beam. So in this approach, we really don't take into account this effect. So we tested in simulations how big errors it introduced. So here are simply tests without photometric errors, simply to test whether the simulations, classic simulations, give us everything is okay. So here is the difference of auto-power spectrum, everything is consistent with zero, so it's also for cross-power spectrum, it's consistent with zero, so it's fine, the simulations works. When we add photometric redshift errors, we have, for auto-power spectrum, we have some deviations, so these two lines correspond one to this so-called naive approach, no correction, and with correction is with the scattering matrix. So with the scattering matrix, fit is better. To see it better, I show this relative difference. So here is even better. We see that this correction with the scattering matrix works pretty well, except this first beam and the last beam. It's because in this last and first beam we have this cap at redshift 0 and cap at redshift 3. And in this deconvolution method, it makes problem in this deconvolution method, so it's not precise. In these two beams, we are not able really to recover redshift distributions. But for other redshift distributions, it looks quite well. But if we don't use the scattering matrix approach, we see that errors are for the 10–15%, right? So quite big errors. And here is for cross-power spectrum. For cross-power spectrum, effect is smaller. We see it's of order of 2%. As I said, it's linear to scattering matrix, while auto-power spectrum is quadratic to scattering matrix, so this effect is stronger for this auto-power spectrum. And here is characters for this larger errors, so we see errors are here even like 30%, so quite really huge. And for auto-power spectrum, not much worse than in previous case. It's also around 2–3%. And so, okay, having this power spectra, we can estimate cosmological parameters. So we use Maxwell-Hakenburg method, and we estimate two parameters: linear galaxy bias, we model it in this way, galaxy bias, and amplitude of cross correlation. So this amplitude of cross correlation is simply proportional to cross power spectrum, some fiducial power spectrum. And we see it's degenerated with this galaxy bias. So we estimate both power spectra and estimate some joint some joint likelihood and estimate these parameters. So here's an example for one of this beam. Here's amplitude and bias. We see quite well. We can recover using the scattering matrix method. So for lambda CDM model, this amplitude should be equal 1, right? This is fiducial Pawel spectrum model. So here are results of this parameters for different redshift beams. And here is relative difference. Here is true value. And we normalize it to standard deviation for a single observation, single realization of this parameter. So we see that without correction for the scattering matrix, errors are for their one standard deviation of this amplitude. And in case of for this larger errors of photometric redshifts, it's even like 3 standard deviations. So it's quite important effect we see for amplitude. And for galaxy bias, it's even stronger. We see it's like 30 standard deviations even, right? For this case and for this, it's like 100, so it's completely off. And we can also, for some future work, we are also thinking to estimate sigma 8 and see effect on sigma 8. So here are some simulations. So here is for this results with scattering matrix. So we see it's perfectly agree with predictions. And I don't show here results without this using scattering matrix, but in principle it's similar, should be similar to this results for this amplitude A, because this amplitude A is in principle proportional to sigma 8. So we can expect that we have also errors for the one standard deviation of sigma 8. And so here are conclusions. So it's using tomographic cross correlations between seeing lensing galaxy surveys is quite useful for tracing time evolution of galaxy structure. We see that systematic errors due to redshift beam mismatch is offered at 10-15% for galaxy out of Pawel spectrum and 2% for cross Pawel spectrum. And for parameters, it's around 1 standard deviation for amplitude and around 10-20 standard deviations for galaxy bias. So we need to use this scattering matrix to correct for this redshift beam mismatch. And we can estimate this scattering matrix using estimate of true redshift distribution, which is, so in this case, we simply need a very accurate estimation of photo set error distribution. Okay, thank you.
Why it is important to assign a galaxy to this spin or the following one, as if you have a correct N of Z that you're using for estimation of the Pawel spectrum, right? If it just turns out that your computation on this point estimate, just gives you the galaxy somewhere else, as long as you have the correct distribution.
Yes, as long as we have correct distribution, then it's not important. So when this error of photometric redshift goes to 0, it will converge to true distribution, and then this effect will be smaller. We see that this effect was larger for the 0.05 than for 0.2. Already for 0.02 is for cross Pawel spectra is around 2%, so it's not so important, but I think it's still worth to correct for this. But for future surveys where we have better estimation of photometric redshift, then probably this effect will not be important. We can neglect it. But for LSST, because this was simulation for LSST, it's still important.
I'll ask a question. So the scatter matrix can give you a more accurate redshift distribution, right? But have you also looked at how it compares with other redshift calibration methods? For example, the machine learning methods that take a spectroscopic sample and try to match it with the photometric sample, or the clustering Z methods where you look at the clustering between spectroscopic redshift galaxies and photometric galaxies?
But I think they give roughly the same errors, like for the 0.02, right? For photometric redshifts, or
so what they try to do is to find the distribution. I guess with photometric, you put the bounds, and then the bounds give you this top hat distributions, right? But we know that there is leakage into the other beams, and so for example, recleansing, what we do is we use these spectroscopic samples, which is like a subsample of our photometric sample, and try to fix the photometric distribution. Just wonder if you've looked at how it compares with your method.
We didn't compare it with this, but I think with this comparison of the spectroscopic distributions is always a problem, but they are more shallow, right? They don't go to very high redshift.
You have to have higher redshift ones. So for example, we have targeted ones where we go up to higher redshift, but of course it's a small sample compared to the full photometric sample. It would be interesting to do a comparison. Okay, any other questions? Right, if not, let's thank Pawel again.